3 column? Well, if you work in a government office, they'll give you somebody who can speak English. Yeah, because those are the best paid jobs in most of the government office. Language skills are not what developing countries lack, people lack. They're good with language skills. What they lack is capital. Things like computers, buildings, and all that stuff. That's what they lack. You take people out of developing countries, I don't care how poor it is, you can find people in developing countries, bring them to the United States, put them into capital, and they're as productive as any American, maybe even better. In their own countries, they can't produce anything, but they don't have the complements. They don't have capital to work with.
That's true.
So, Nixon said that? No. But what I'm trying to tell you is that if you know this, you can go anywhere in the world in computer regression, with or without computers. You just got to know the scheme. If you depend too much on computers, you'll be lost as a consultant in developing countries. I was an advisor to the Philippines. In the Philippines, they had really good economists. Guys had PhDs from Yale and Harvard and all over the place. And they had fantastic computer programmers. They would program for 75 cents an hour and work all weekend, 75 cents an hour. But they couldn't put it all together because they didn't have the computers that they needed to do the programming. The lousy programs, lousy computers. The few computers they had were outdated, not working half the time, and so on. All right. But I think you all get the scheme now, how to do that. You can expand that matrix as much as you want to get as many coefficients as you want, depending on the model. The next thing that we have to look at is evaluating the coefficients. So let's look at that problem. I'll first do it with, how many people here have had statistics? 1, 2, 3, 4, 5, 6, 7. Less than half. All right. Let's take the simple case first. The estimate B was given by the covariance between x and y over the variance of y. Now this is estimated by the summation x, y, minus n x bar y bar. The summation x squared minus n x bar. I think we arrived at that formula last time. Right? Now we can rewrite this, and you can prove this to yourself. The summation of x minus x bar and y minus y bar equals that. And this can be also rewritten as summation of x minus x bar squared. Now I want to take the first part, the top part first. We can rewrite this summation of x minus x bar of y minus y bar is a subscript here. Sometimes I admit it, just I'm lazy. We can rewrite this by multiplying this by the terms. This is equal to the summation of xi minus x bar times yi minus the summation of xi minus x bar times y bar. This is y bar here. What I did was expand that binomial. Now we can then take the summation and put it in between. We get the summation of xi minus x bar times yi minus the summation of xi x bar times y bar. Now the y bar is a constant. It's not subscripted. So we can take that out. We have y bar as the summation of xi minus x bar. This portion is equal to this. All right? Now if we take the summation sign here and put it against these two, we'll have equals y bar times the summation of xi minus the summation of x bar. The summation of x bar is simply equal to x bar plus x bar plus x bar, and so on, x bar. And you have n of these. So that's just equal to nx bar. This portion can be replaced by nx bar. And the summation of xi is equal to n times the summation of xi divided by n. Because if you multiply by n and divide by n, you don't change the expression. And that's equal to n. So basically, these two pieces in here are nx bar, which means they cancel each other out. So this whole term becomes equal to 0. This portion over here equals 0. So, and going back to our equation over here then, V, that is equal to summation of xi minus x bar times y over summation of xi minus x bar squared. This is the estimate that we're looking for in simple case. We're dealing with the case now where y is equal to a plus bx. Now this model, we made the following assumptions. The x's are exogenous, which means that you pick them. They're not random variables. They're the decision variables that you pick. All right? Epsilon I is a random variable. And it has a distribution like a normal distribution. It's normal, but mean 0 with some standard deviation sigma squared. So mu of epsilon I equals 0, and the distance from here to here is 6. We also have the covariance with epsilon I and epsilon j equals to 0. That means there's no serial correlation. If we take our model, the expected value of yi equals the expected value of a plus b xi plus epsilon I, and that's equal to the expected value of a plus the expected value of bxi plus the expected value of epsilon. So that's equal to a plus bxi, and the expected value of epsilon I is this mean uxi, that's 0. So yi, the mean of yi is equal to a plus bx xi, period. Yi is a random variable. Because it's a random variable, it has a mean. The mean is this line. The variance of yi will be the variance of a plus b xi plus epsilon I. Now, if we bring the variance operator in here, we have the variance of a, but a is a constant. Can the constant vary? No, 0. bxi is also a constant, so this variance is 0. The only variance is this, epsilon I, but we know what the variance of that is, the sigma square. The variance of yi is sigma square. Now, in order to evaluate b, we have to recognize, first of all, that b is a random variable. The reason why it's a random variable because it's a function of yi. And yi is a random variable because it's a function of epsilon. So b is a random variable. So what we want to compute from b is this error. We want to compute what is the error of b. Because we're estimating it, and now we'd like to get some kind of feel for what kind of error might be involved in that estimate. And the way we do that is by computing the variance for b. Is there anybody here who works in finance?
This guy.
In finance, it's all about getting the variances of the beta coefficients. These high-priced guys on Wall Street who work in finance are people who know how to compute the error involved in an investment. It's all about this, getting the variance on the coefficients of the investment.
Is that true?
This is something you want to, if you want to go ahead and make money on Wall Street, get into finance. If you go up here on the 6th floor, where they have the MBA program, if you go for an MBA, about 80% of the MBA students go for finance. The only reason why they go there, not because they love variance, they go there because they love money.
Of course.
If they have to learn variance and to get money, then they'll learn variance with the money that they want, right? They also have a master's degree in quantitative finance, where you don't have to study the other things that you get in an MBA, like management and the other stuff. You concentrate only on the variances of these students. And what they call derivatives down on the street. They put together derivative packages. It's all based on these variances. It's all based on errors. Okay, so to get the variance of B, we have to get the variance of that. Which B is equal to that. Now, in the variance operator, when you take the constant out, the constant is always squared. So this whole bottom here, all x's, is a constant. You take that out of the variance operator. You take that out of the variance operator, it's become the summation is xi minus x bar squared. Squared. And now we can put the variance operator inside the summation zone. That. What I do is bring the summation sign out and bring that in. All right? Now, since this is a constant, you can take it out of the variance operator and square it. That comes out. Times the variance of yi. But we know what the variance of yi is. We just computed it over here. It's a constant, sigma squared. So we can replace this equal to sigma squared, which is the variance of epsilon. And these two cancel out, and we come up with the formula for variance of B. Here. And that's the variance. And I can show you how to get A, the variance of A. Remember that A is equal to y hat minus B x bar. And this is the variance of that, and this is the variance of that. It's a little more complicated, but it takes about 5 minutes. I'm not going to go through it because I'm not going to ask you to compute these things. I just want to show you that they're very important. They're there, all right? The variances. Now, Once we know the variance of B, then we have a good handle about the error involved in estimating, plus or minus the variance. But another way we look at that, at B, is to set up a test, a hypothesis test. The problem is we don't really know sigma squared. We estimate sigma squared with the thing. So really, the variance would be what comes out to this S squared. So the summation of y. Now S squared estimated by adding up epsilon 1 squared, epsilon 2 squared, n squared and divided by n minus 1. And no, sorry, n minus 2 because we have two estimates. A and B, n minus 2. So we like to set up a hypothesis test. The null hypothesis goes to null hypothesis, H1, is that B is equal to 0. Against the alternative hypothesis, H1, that B is not equal. Now we set up this test using a t-test. The t-test is equal to B divided by the standard error of B. Where the standard error of B is this thing here, and B is the estimated coefficient. And the way we test that, if this is the t-distribution, how many people know the origin of this t? How many Irishmen? This came from Ireland. Right? And it was discovered by a brewery worker. At Guinness. A brewery worker at Guinness. His name was Dawson. Right? And he invented this test, statistical test. But he worked at a brewery at Guinness. But apparently was a highly educated guy. Right there. And then when he submitted to an academic journal, he didn't want to say he was not an academic. He just put down student of statistics. And he presented this test, this t-test. The t-test is probably the second most used test, maybe the first most used test in statistical hypothesis testing in the world. It's used every day, millions of times, by economists, sociologists, psychologists, anybody in the social sciences uses statistics. They use the t-test. And when economists use t-test, they don't do it in a very strict fashion. All they do is look at the value of the t-distribution that we get over here. This is the estimated parameter, and this is the b, the variance, the standard deviation value, it's very little variance. And we check to see if it's above 2 or less than minus 2. There's very few true t random variables will be above 2 or less than minus 2. If it's here, if the t-value we get is there, we reject h to 0. We reject h to 0. In here, we accept it. Now, if we reject h sub 0, it means we're accepting h1. When you accept h1, you say, well, estimated b that we got is not equal to 0. If we accept h sub 0, we say the b is 0. Now, if the b is 0, you see what it does to the equation. You have an equation like this: y is a plus bx. And from a statistical point of view, you might as well have put 0 over here. And the equation will look like y is equal to a. And the equation is not very much useful. So that's why we have that test. If it says it's not equal to 0, we say, okay, this is all right. We'll live with that. So whenever you do a regression, after you get the estimated parameters, you have to check these t-tests to see how well they, whether they're equal to 0 or not, from a statistical point of view. And that gives you some sense of confidence. But I want to now give you an example of how we put all of this together on computers for economics. All right?
Piece of shit. Smallest country in Africa. One of the smallest cities in Africa. Oh shit. It's big. It's just so down. Yeah, it's just the river. It's not like the river. It's not the river. And then there's one here. It's surrounded by sun.
We'll go back here.
It used to be one country. The British, you know, like 25, you know. We discovered all that. And the population is on the community. That's what I want to go back to citizenship. The 2 million population is discovered all. Once they start talking about the average cost of living will be better than Saudi Arabia. I found out what is it? People like me who've been out for a long time. More than 40 years, you know. Of course, I still have my passport. The real estate of the country that is being my grandfather, the grandfather side of the first time and the young go back. Of course, they know it was. The early president is from the countryside. Only thing is that he was living with the guy that was politics started. That guy, he was my father, who got him a job. But you never get involved with it. Yeah, you know, the kid. Such an image. And you use it all is used by the investments of the and he was not able to register. And the reason the British maintained.
Now, we have some data here for a firm that makes casement windows. Now, one of their products is a little screen that goes over the casement window. Right? And they call that model number 245. And it's the window screen that goes over the little casement window. Everybody knows what I mean by casement window. The little window that you see in basements. Basements have a little window, the casement window. Now, the firm has their own business. This particular product. In 1995, they sold 40,000, 96, 60, and so on. 2006, they sold 65,000 units. And their price was $20 in 1995, and it fluctuated. It was $35 in 2006. Now, the market size that they're looking at was like 2 million households in 95. Up to 4.8 million households in 2006. And the competition's price, that is other people who make the same screen window, are over there on the right. Now, what we want to do is first of all set up a forecasting equation.